Welcome back to the channel. Today is episode 24 of me doing statistics. Um, yep, today we'll be doing the unit test on unit 10. So just looking through, it's been about a week since I've last uploaded, which is fine. But looking through here, confidence intervals, significance tests, tests for population proportions, potential errors when performing tests, confidence intervals, and then looking at the difference of two proportions. Okay, let's get started. So I'm probably gonna get this wrong, but it'll be fine. We'll go back and forth. Strong evidence that's proportion. Okay. Type 2 error. Fail to reject. Fail to reject. They don't consider building a new cafeteria when they should have. Oh shit. P versus P hat. I'm pretty sure it's P, not P hat. Less than 0.25. P1 minus P2 versus 0. Okay. 36 over 75. 0.48. So it's between B, D, and E. Mm-hmm. Hmm. $56 over 175. 0.32 should be the same in both. N1, N2. I think it'd be this then. B. Let's try it. If I get wrong, it's fine. Which of the following is a 90% confidence interval based on Melina samples? Okay, so P1 minus P2. Okay, so all of this is right. We can narrow it down by z-score for the confidence interval, 90%. Hopefully this loads. %5 on both sides, so 95%. 0.95. 1.645. Okay, so remove these options. All of these are the same apart from the standard error. Oh, B1, Q1. The fuck is Q1? Oh, I see. Okay. 0.64. It's never minus. Standard deviation, standard error is never minus. 0.64, 0.36. I think it's B again. It's probably B. Which conditions for performing this type of test did Liam's sample meet? Kind of test, okay. SRS, it's random. He's trying to make an inference about population proportion, okay. Expected counts of successes and failures are both sufficiently large. It needs to be at least 10. So 50, 0.09, that's 9%. Even 10% of 50 isn't 10, so fail that. Individual observations can be considered independent. 50 people from our city. It's a large city, so 50 is probably less than 10%. Based on the interval, what do we know about the corresponding p-value and conclusion at the alpha 0.05 level of significance? Okay. So from the confidence interval, we need to look at corresponding p-value. Okay. Trying to remember how to do this question. Let's see how to do it. Do some help here. Call a friend. Since 95% CI doesn't include our null hypothesis value, we know that P is 0.05. We can reject the null hypothesis at the 5% significance level. Okay, I think what we have to do here is write a new hypothesis. Okay, so H0, HA would be is no difference. So P equals 0, P Yep, P0, P not equals 0, where P is the difference. So since this includes 0, and this is 95% confidence interval, we can safely reject the null hypothesis. Oh wait. Easy. That was so confusing. What is the critical z value z for constructing an 80% confidence? Okay, z score table. So 10% on both sides. 90%. 1.18. 1.282. P is less than 0.8. Makes sense. 0.1, 0.07 is less. 80%. Random sample. 50 women in Albania. And then there aren't enough failures. test. Calculate the test statistic for their significance test. Z test statistic. Okay, this is the one. One sample Z test. That's what I needed. Okay, so P hat minus PO 0.8. N is equal to 64. Doesn't feel right. Here, let's go with that. Wow. Which of the following represents the p-value for their test? Hmm. No, it's saying z less than, okay, so z less than 0.45. It's this one, I'm pretty sure. Because this is p naught. Yep. What is the p-value associated with these sample results? Okay. P equals P given POS equals PGB or P equals 0. Hmm. P1 minus P2. Oh wait, what do I do? 300, 200. This can also be expressed as P, the probability of the sample statistic given the H naught, given H naught. The statistic is doing that, so we're using H naught. Okay. 0.9778. Okay, just give me a sec. It's a two-tailed test, so we do 1 minus times 2. 0.0444. It's below 0.05, but it's above 0.01. Hell yeah. Okay. Break time. Okay, let's have a look. If we assume p hat equals 0.4, what is the smallest sample size required to obtain the desired margin of error? Hmm. Think. 'Kay, I think this is 1.96. Hmm. So, oh wait, I think I'm supposed to. Oh, dumb. I'm supposed to substitute these numbers in. It's 1.96. It's greater than 5%. Oh, still too big, 6%. 0.055, still too high. Yep, that's just below 5%, so 369. Nice. Appropriate hypothesis for the company's significance test. Okay. More than 10%. Okay. So it's 10%, no difference. Greater than 10% difference. Based on the sample, which of the following is a 95% confidence interval for the proportion of computers that have the defect? Yeah, right, okay. 12 over 200, 0.06. Cross these two answers out. And then the z-score is different. 95%. 1.96. 2.5 on each side. True mean. So which situation has the highest power? Upping the alpha decreases the chance of type 2 error. Increases the chance of type 1 error. Hmm. The true mean is actually 420 ppm. Okay. If the true mean is further away from the null hypothesis, it would mean that we more easily reject the null hypothesis instead of wrongly ignoring it. Which of the following is an appropriate set of hypotheses for their significance test? Okay. Immediately cross this one off. Is working any differently? So it's any differently, meaning either direction. It's probably that. Which of the following are conditions for this type of test? Two sample z-test. To see if the proportion who support the change is significantly different between the two groups, okay? Needs to be chosen randomly. Oh wait, hold on. Hi. Good, good. 1:30, so 1:30? Yeah, it sounds good. Yep, no worries. See ya. Parents in each sample can be considered independent, and the samples themselves are independent. Yes. Parents from each school are chosen randomly. Yes. Oh, fuck. Not sure if that's a trick condition. The expected counts of parents who support the change and do not support the change. Okay. Two sample z-test conditions. Random sampling. Independence of samples. Normal distribution. Okay, we're gonna go with it. Oh gosh. X bar was 2.96 mm. X bar is sample. Okay, so 2.96, given that nu is actually 3 mm, X bar, probability of that. How do we calculate this? What is the approximate p-value of the test? Sample result was X bar 2.96. Oh, I see. I think. Okay, we have 75 samples, and then our alternative hypothesis is a two-sided one or two-tailed one. Our sample result was 2.96, and our null hypothesis is that it's 3 mm. So the difference between the observed statistic and the hypothesized parameter is 0.04. So if we look at 3, where is 3? 8, 9. 3 is over here. So 2.96. It's kind of confusing. So it's like here, 3 up to here. Hmm. Hmm. Oh, the standard deviation is 0.2. Okay, we'll go with that. Yeah, perfect. Ooh, that is satisfying. Okay, we will take a break because we're starting a new unit. Introduction to T statistics. Okay, that's fine. Take a break now. Okay. Close this stuff now.
We have already seen a situation
Wait,
multiple times.
so that was unit 10. A lot of what we did had to do with confidence intervals and conducting tests, like a one sample Z test, two sample Z test. I think that's what they're called. And building on the previous units, we learned about calculating the area under a curve and the intuition behind significance testing and interpreting experiment results. What other things have we learned about? And for these tests, they pretty much follow just the assumptions of many kinds of tests and statistical techniques. So, independent, random, hmm, not how would I say this? Independence, the random assumption, and normality. That's the one. It's forgetting that. Okay, now we'll be moving on to Unit 11. I don't have a slide for Unit 11, which is an oopsie on my part, but okay. It says here, inference for quantitative data means. Okay, so we were doing categorical data proportions. No, it's quantitative data means, okay. From quality control to predicting the amount of snowfall that will result from an upcoming blizzard, this unit will give you the tools to calculate an inference from a population mean to make predictions about quantitative outcomes. Okay, sounds reasonable. Let me just read through this. Okay. Inference from a population mean to make predictions about quantitative outcomes. Okay.
Seen a situation multiple times where there's some parameter associated with a population. Maybe it's the proportion of a population that supports a candidate. Maybe it's the mean of a population, the mean height. We have already seen a situation multiple times where there's some parameter associated with a population. Maybe it's the proportion of a population that supports a candidate. Maybe it's the mean of a population, the mean height of all the people in the city. And we've determined that it's unpractical, or there's no way for us to know the true population parameter, but we could try to estimate it by taking a sample size. So we take n samples, and then we calculate a statistic based on that. We've also
Unsample statistic. Generate a confidence
seen that
interval.
not only can we calculate the statistic, which is trying to estimate this parameter, but we can construct a confidence interval about that statistic based on some confidence level. And so that confidence interval would look something like this. It would be the value of the statistic that we have just calculated, plus or minus some margin of error. And so we'll often say this critical value, z, and this will be based on the number of standard deviations we want to go above and below that statistic. And so then we'll multiply that times the standard deviation of the sampling distribution for that statistic. Now, what we'll see is we often don't know this. To know this, you oftentimes even need to know this parameter. For example, in a situation where the parameter that we're trying to estimate and construct confidence intervals for is, say, the population proportion. What percentage of the population supports a certain candidate? Well, in that world, the statistic is the sample proportion. So we would have the sample proportion plus or minus z star times, well, we can't calculate this unless we know the population. A situation where the parameter that we're trying to estimate and construct confidence intervals for is, say, the population proportion. What percentage of the population supports a certain candidate? Well, in that world, the statistic is the sample proportion. So we would have the sample proportion plus or minus z star times, well, we can't calculate this unless we know the population proportion. So instead, we estimate this with the standard error of the statistic, which in this case is p hat times 1 minus p hat, the sample proportion times 1 minus the sample proportion over our sample size. If the parameter we're trying to estimate is the population mean, then our statistic is going to be the sample mean. So in that scenario, we are going to be looking at our statistic is our sample mean plus or minus z star. Now, if we knew the standard deviation of this population, we would know what the standard deviation of the sampling distribution of our statistic is. It would be equal to the standard deviation of our population times the square root of our sample size. But we often will not know this. In fact, it's very unusual to know this. And so sometimes you will say, okay, if we don't know this, let's just figure out the sample standard deviation of our sample here. So instead, we'll say, okay, let's take our sample mean plus or minus z star times the sample standard deviation of our sample, which we can calculate, divided by the square root of n. Now, this might seem pretty good if we're trying to construct a confidence interval for our sample, for our mean, but it turns out that this is not so good. Because it turns out that this right over here is going to actually underestimate the actual interval, the true margin of error you need for your confidence level. And so that's why statisticians have invented another statistic. Instead of using z, they call it t. Instead of using a z table, they use a t table. And we're going to see this in future videos. And so if you are actually trying to construct a confidence interval for a sample mean, and you don't know the true standard deviation of your population, which is normally the case, instead of doing this, what we're going to do is we're going to take our sample mean, plus or minus, and our critical value, we'll call that t star, times our sample standard deviation, which we can calculate, divided by the square root of n. And so the real functional difference is that this actually is going to give us the confidence interval that actually has a level of confidence that we want. If we want a 95% level of confidence, if we keep computing this over and over again for multiple samples, that roughly 95% of the time, this interval will contain our true population mean. And to functionally do it, and we'll do it in future videos, you really just have to look up a t table instead of a z table.
Let's watch this video from Khan Academy. That's statistics and probability.
I want to use this video to kind of make sure we intuitively and otherwise understand the difference between a z statistic, something I have trouble saying, and a t statistic. So in a lot of what we're doing in this inferential statistics, we're trying to figure out what is the probability of getting a certain sample mean. So what we've been doing, especially when we have a large sample size, so let me just draw a sampling distribution here. So let's say we have a sampling distribution of the sample mean right here. It has some assumed mean value. It has some assumed mean value and some standard deviation. And what we want to do is any result that we get, let's say we get some sample mean out here, we want to figure out the probability of getting a result at least as extreme as this. So you can either figure out the probability of getting a result below this and subtract that from 1, or just figure out this area right over there. And to do that, we've been figuring out how many standard deviations above the mean we actually are. And the way we figure that out is we take our sample mean, we subtract from that our mean itself, we subtract from that what we assume the mean should be, or maybe we don't know what this is. The mean should be, and then we divide that by the standard deviation of the sampling distribution. We divide that by the standard deviation of the sampling distribution.
Yeah, okay.
This is how many standard deviations we are above the mean.
Ah. Nope, don't get it.
That is that distance right over there. Now, we usually don't know what this is either. We normally don't know what that is either. And the central limit theorem told us that, assuming that we have a sufficient sample size, this thing right here, this thing is going to be the same thing as the sample is going to be the same thing as the standard deviation of our population, the standard deviation of our population divided by the square root of our sample size. So this thing right over here can be rewritten as our sample mean minus the mean of our sampling distribution of the sample mean divided by this thing right here, divided by our population mean divided by the square root of our sample size.
Okay, that formula is more familiar. Central limit theorem.
And this is essentially our best sense of how many standard deviations away from the actual mean we are. And this thing right here, we've learned before, is a z-score, or when we're dealing with an actual statistic when it's derived from the sample mean statistic, we call this a z-statistic, And then we can look it up in a z-table or in a normal distribution table to say, what's the probability of getting a value of this z or greater? So that would give us that probability. So what's the probability of getting that extreme of a result? Now, normally when we've done this in the last few videos, we also do not know what the standard deviation of the population is. So in order to approximate that, we say that the z-score is approximately, or the z-statistic is approximately going to be, so let me just write the numerator over again, we estimate this using our sample standard deviation. We estimate it using our, let me just in a new color, using our sample standard deviation. And this is okay if our sample size is greater than 30. Or another way to think about it is this will be normally distributed if our sample size is greater than 30. Even this approximation will be approximately normally distributed. Now, if your sample size is less than 30, especially it's a good bit less than 30, all of a sudden this expression will not be normally distributed. So let me rewrite the expression over here. Sample mean minus the mean of your sampling distribution of the sample mean divided by your sample standard deviation over the square root of your sample size. We just said if this thing is well over 30, or at least 30, then this value right here, this statistic, is going to be normally distributed. If it's not, if this is small, if that is small, then this is going to have a t-distribution. And then you're going to do the exact same thing you did here, but now you would assume that the bell is no longer a normal distribution. So in this example, it was normal. All of the z's are normally distributed. Over here in a t-distribution, and this will actually be a normalized t-distribution right here because we subtracted out the mean. So in a normalized t-distribution, you're going to have a mean of 0. And what you're going to do is you want to figure out the probability of getting a t-value at least this extreme. So this is your t-value you would get, and then you essentially figure out the area under the curve right over there. And so a very easy rule of thumb is calculate this quantity either way. If you have more than 30 samples, if your sample size is more than 30, your sample standard deviation is going to be a good approximator for your population standard deviation. And so this whole thing is going to be approximately normally distributed. And so you can use a z-table to figure out the probability of getting a result at least that extreme. If your sample size is small, then this statistic, this quantity, this is going to have a t-distribution. And then you're going to have to use a t-table to figure out the probability of getting a t-value at least this extreme. And we're going to see this in an example a couple of videos from now. Anyway, hopefully that helped clarify some things in your head about when to use a z-statistic or when to use a t-statistic.
We have already seen a situation multiple times where there is some parameter associated with a population. So that will sample which of the portions one we're trying to and be equal to figure out my full not interval. Instead of Bruce can keep this and just have to look up a t-table instead of a z-table. That t star times our sample standard deviation, which we can calculate, divided by the square root of n. Now, this might seem pretty good. if we're trying to construct a confidence interval for our sample, for our mean. But it turns out that this is not so good, because it turns out that this right over here is going to actually underestimate the actual interval, the true margin of error you need for your confidence level. And so that's why statisticians have invented another statistic. Instead of using z, they call it t. Instead of using a z table, they use a t table. And we're going to see this in future videos. And so if you are actually trying to construct a confidence interval for a sample mean, and you don't know the true standard deviation of your population, which is normally the case, instead of doing this, what we're going to do is we're going to take our sample mean, plus or minus, and our critical value, we'll call that t star, times our sample standard deviation, which we can calculate, divided by the square root of n. And so the real functional difference is that this actually is going to give us the confidence interval that actually has a level of confidence that we want. If we want a 95% level.
Okay. You want to stay up here? You just keep doing your work.
Confidence, if we keep computing this over and over again for multiple samples, that roughly 95% of the time,
let's keep working
this
until
interval
like 11
will
minutes.
contain our true population mean. And to functionally do it, and we'll do it in future videos, you really just have to look up a t table instead of a z.
But what is the difference of a z and a t table? The individual use of one or the other has to do with a lot of different conditions, such as assumptions of normality, whether or not the standard deviation is already known, and whether you are comparing independent samples. But the point is that essentially when you are really far away from the center of the distribution, due to how normality works, it's very unlikely to have occurred by chance. So being at the extremes generally indicates something statistically significant, which leads to p-value is what determines whether you reject or accept the null hypothesis. In very basic terms, it's the probability of being wrong when you reject the null hypothesis. You determine the significance level alpha that you want depending on how critical the test is. For instance, if you want a significance level of 0.05, okay. I do not understand. Okay.
In a previous video, we talked about trying to estimate a population mean with a sample mean, and then constructing a confidence interval about that sample mean. And we talked about different scenarios. We could use a z-table plus the true population standard deviation, and that actually would construct pretty valid confidence intervals. But the problem is you don't know the population standard deviation. And so you might try to use a z-table to find your critical values, plus the sample standard deviation. But what we talked about is that this doesn't actually do a good job of calculating our confidence intervals. And we're going to see that experimentally in a few seconds. And so instead, we have something called a t-statistic, where if we want our critical value, we use a t-table instead of a z-table, and then we use that in conjunction with our sample standard deviation, and then all of a sudden we are actually going to have pretty good confidence intervals. To make this a little bit more real, let's look at a simulation. So this is a scratch pad on Khan Academy made by Khan Academy user Charlotte Owen. And the whole point there is to see what our confidence intervals look like with these different scenarios. So let's say we have a true population mean of 2.0 for some, let's say it's the average number, the mean number of apples people eat a day. The true population mean is 2. That seems high, but maybe it's in a certain country that has a lot of apples. And let's say we know that the population standard deviation is 0.5. And we're going to create confidence intervals with the goal of having a 95% confidence level. And we're going to take sample sizes of 12. So first, we can construct our confidence intervals using z and sigma, which is a legitimate way to do it. And so let's just draw a bunch of samples here. And so we do see that it looks like it is roughly 95% when we keep making these samples and constructing these confidence intervals, that 95% of the time, these confidence intervals contain our true population mean. So these look like a good confidence intervals. But what we've talked about is, normally when you're doing this type of thing, this type of inferential statistics, you don't know the population standard deviation. You don't know sigma. So instead, you might be tempted to use z with our sample standard deviations. But if you look at that for these exact same samples we just calculated, notice now when we did it over and over again, we've done this 625 times. In this scenario where we keep calculating the confidence intervals with z and s, the true population mean is contained in the intervals only 92.2% of the time. And we could keep going. So we have a much lower hit rate than we would hope to have if we were actually using z and sigma. Now, what's neat is if we use a t table, notice this is getting much closer. And this is neat because with a t table and something that we can actually get from the sample, so it contained in the where we keep calculating the confidence interval, might be tempted to use z with our sample standard deviations. But if you look at that for these exact same samples we just calculated, notice now when we did it over and over again, we've done this 625 times. In this scenario where we keep calculating the confidence intervals with z and s, the true population mean is contained in the intervals only 92.2% of the time. And we could keep going. So we have a much lower hit rate than we would hope to have if we were actually using z and sigma. Now, what's neat is if we use a t table, notice this is getting much closer. And this is neat because with a t table and something that we can actually get from the sample standard deviation, we're actually able to have a pretty close hit rate to what we would have if we actually knew the population standard deviation. So that's the value of t and t statistics. And we're going to give more and more examples, including using a t table in future videos.
Then why wouldn't we always just use these? Wizardry. Choice between using t with sample standard deviation t and s and using z with population standard deviation z and sigma depends on the context and the available information. When the population standard deviation is known, using z and sigma may be preferable because it eliminates the need to estimate the standard deviation from the sample. However, when the population standard deviation is unknown, t and s are used as the t distribution provides more accurate confidence intervals by accounting for the variability introduced by using the sample standard deviation. Okay, so z when the standard deviation of the population is known, t when it's not. So t and sample standard deviation, or z and sigma. Sigma is the symbol for population standard deviation, or the standard deviation parameter. S is the standard deviation for a sample. Okay. They should have made it like S and S bar. So that shit is confusing.
Flavia wanted to estimate the mean age of the faculty members at her large university. She took an SRS, or simple random sample, of 20 of the approximately 700 faculty members, and each faculty member in the sample provided Flavia with their age. The data were skewed to the right with a sample mean of 38.75. She's considering using her data to make a confidence interval to estimate the mean age of faculty members at her university. Which conditions for constructing a t interval have been met? So pause this video and see if you can answer this on your own.
Random sample, normal, all of them. Actually, hold on. Okay, it's random. 20 of the 700 faculty members. I don't know how the second condition could be met.
Okay, now let's try to answer this together. So there's 700 faculty members over here. She's trying to estimate the population mean, the mean age. She can't talk to all 700, so she takes a sample, a simple random sample of 20. So the n is equal to 20 here.
I really
From
like
this
these
20,
drawings.
she calculates a sample mean of 38.75. Now, ideally, she wants to construct a t interval, a confidence interval using the t statistic. And so that interval would look something like this. It would be the sample mean plus or minus the critical value times the sample standard deviation divided by the square root of n.
Yeah.
And we use a t statistic like this and a t table and a t distribution when we are trying to create confidence intervals.
So it's like calculating the test statistic for, population proportion or with z, but we just use t instead. And also we use sample standard deviation
for means where we don't have access to the standard deviation of the sampling distribution, but we can compute the sample standard deviation. Now, in order for this to hold true, there's three conditions, just like what we saw when we thought about z intervals. The first is that our sample is random. Well, they tell us that here, that she took a simple random sample of 20. And so we know that we are meeting that constraint, and that's actually choice A. The data is a random sample from the population of interest. So we can circle that in. So the next condition is the normal condition. Now, the normal condition when we're doing a t interval is a little bit more involved, because we do need to assume that the sampling distribution of the sample means is roughly normal. Now, there's a couple of ways that we can get there. Either our sample size is greater than or equal to 30. The central limit theorem tells us that then our sampling distribution, regardless of what the distribution is in the population, that the sampling distribution actually would then be approximately normal. She didn't meet that constraint right over here. Here, her sample size is only 20. So far, this isn't looking good. Now, that's not the only way to meet the normal condition. Another way to meet the normal condition, if we have a smaller sample size, smaller than 30, is one, if the original distribution of ages is normal, so original distribution normal, or even if it's roughly symmetric around the mean, so approximately symmetric. But if you look at it, they tell us that it has a right
Skewed to the right, yep.
skewed.
So not
They say the data were skewed to the sample is where you could have faculty members who are 30 years older than this, 68 and 3/4. Well, think about it. It's not going to be, your likely sample is not symmetric. And the original distribution is unlikely to be normal. Think about it. It's not going to be, you're likely to have people who are, you could have faculty members who are 30 years older than this, 68 and 3/4, but you're very unlikely to have faculty members who are 30 years younger than this. And that's actually what's causing that skew to the right. So this one does not meet the normal condition. We can't feel good that our sampling distribution of the sample means is going to be normal. So I'm not going to fill that one in. Choice C, individual observations can be considered independent.
I think the way you assume normality for inference on categorical data is different. So this is this has to do with the distribution itself, whereas the other one has to do with the expected numbers of successes and failures.
So there's two ways to meet this constraint. One is if we sample with replacement. Every faculty member we look at, after asking them their age, we say, hey, go back into the pool, and we might pick them again until we get our sample of 20. It does not look like she did that. It doesn't look like she sampled with replacement. And so even if you're sampling without replacement, the 10% rule says that, look, as long as this is less than 10% or less than or equal to 10% of the population, then we're good. And the 10% of this population is 70. 70 is 10% of 700. And so this is definitely less than or equal to 10%. And so it can be considered independent. And so we can actually meet that constraint as well. So the main issue where our t-interval might not be so good is that our sampling distribution, we can't feel so confident that that is going to be normal.
Okay, fair enough. Random, normal, independent, RNI. Let's try an exercise. Which samples satisfy the normal condition for constructing a t-interval? Neither sample. I would say sample A maybe. That's roughly. Sample B. N equals 36. Maybe both samples roughly symmetric. SRS. Random 100 births. Sampling distribution is approximately. Wait, hold on. Infants in Somalia. Okay, all of it. Only sample B. This one is left skewed. Let me see. Break time. And we're back. Okay. It's freaking cold this morning, guys. Okay.
We are asked, what is the critical value T star or T asterisk for constructing a 98% confidence interval for a mean from a sample size of n is equal to 15 observations? So just as a reminder of what's going on here, you have some population. There's a parameter here. Let's say it's the population mean. We do not know what this is, so we take a sample. Here we're going to take a sample of 15. So n is equal to 15. And from that sample, we can calculate a sample mean. But we also want to construct a 98% confidence interval about that sample mean. So we're going to go take that sample mean, and we're going to go plus or minus some margin of error. Now, in other videos, we have talked about that we want to use the t-distribution here because we don't want to underestimate the margin of error. So it's going to be t star times the sample standard deviation divided by the square root of our sample size, which in this case was going to be 15, so the square root of n. But what they're asking us is, well, what is the appropriate critical value? What is the t star that we should use in this situation? And so we're about to look at I guess we call it a t table instead of a z table. But the key thing to realize is there's one extra variable to take into consideration when we're looking up the appropriate critical value on a t table. And that's this notion of degree of freedom. Sometimes it's abbreviated df. And I'm not going to go in depth on degrees of freedom. It's actually a pretty deep concept. But it's this idea that you actually have a different t distribution depending on the different sample sizes, depending on the degrees of freedom. And your degree of freedom is going to be your sample size minus 1. So in this situation, our degree of freedom is going to be 15 minus 1. So in this situation, our degree of freedom is going to be equal to 14. And this isn't the first time that we have seen this. We talked a little bit about degrees of freedom when we first talked about sample standard deviations and how to have an unbiased estimate for the population standard deviation. And in future videos, we'll go into more advanced conversations about degrees of freedom. But for the purposes of this example, you need to know that when you're looking at the t distribution for a given degree of freedom, your degree of freedom is based on the sample size, and it's going to be your sample size minus 1 when we're thinking about a confidence interval for your mean. So now let's look at the t-table. So we want a 98% confidence interval, and we want a degree of freedom of 14. So let's get our t-table out. And I actually copy and pasted this bottom part, moved it up so you can see the whole thing here. And what's useful about this t-table is they actually give our confidence levels right over here. So if you want a confidence level of 98%, you're going to look at this column. Look at this column right over here. Another way of thinking about a confidence level of 98%, if you have a confidence level of 98%, that means you're leaving 1% unfilled in
sides, yep.
at either end of the tail.
Like
and so if you're looking at your t-distribution, everything up to and including that top 1%, you would look for a tail probability of 0.01, which is, you can't see it right over there, let me do it in a slightly brighter color, which would be that tail probability to the right. But either way, we're in this column right over here. We have a confidence level of 98%. And remember, our degrees of freedom. Our degree of freedom here is, we have 14 degrees of freedom. And so we'll look at this row right over here. And so there you have it. This is our critical t-value, 2.624. And so let's just go back here. 2.264 is this choice right over here. And we're done.
Okay. Let's pull out the t-table. Degrees of freedom would be 11 because 12 minus 1, 90% confidence. 1.796. 9 at 99%. 3.25. So it's pretty much just like a 795, just like a this z table, but you know, with confidence levels and degrees of freedom, instead of you manually picking out the probability. And C-score with the probability of your confidence interval. Okay. 95, 8, 2.306, 599, 99, 5, 4, 0, 3, 2.
A nutritionist wants to estimate the average caloric content of the burritos at a popular restaurant. They obtain a random sample of 14 burritos and measure their caloric content. Their sample data are roughly symmetric with a mean of 700 calories and a standard deviation of 50 calories. Based on this sample, which of the following is a 95% confidence interval for the mean caloric content of these burritos? So pause this video and see if you can figure it out.
So I think that the T, no. The confidence interval for a mean uses a T interval, okay. So it'd be the T value times sample standard deviation over N, or in degrees of freedom, I'm not sure.
They are a mean by the standard population standard deviation. That's why we're using a t statistic. Z sample standard deviation. And if we use that, if we use sigma, which is a population parameter, then we could use a z statistic right over here. We would use a z distribution. But since we're using this sample standard deviation, that's why we're using a t statistic. But now let's do that. So what is this going to be? So our sample mean is 700. They tell us that. So it's going to be 700 plus or minus. So what would be our critical value for a 95% confidence interval? Well, we will just get out our t-table. And with a t-table, remember, you have to care about degrees of freedom. And if our sample size is 14, then that means you take 14 minus 1. So degrees of freedom is n minus 1. So that's going to be 14 minus 1 is equal to 13. So we have 13 degrees of freedom that we have to keep in mind when we look at our t-table. So let's look at our t-table. So 95% confidence interval and 13 degrees of freedom. So degrees of freedom right over here. So we have 13 degrees of freedom. So that is this row right over here. And if we want a 95% confidence level, then that means our tail probability. Remember, if our distribution, let me see if I'll draw it really small, little small distribution right over here. So if you want 95% of the area in the middle, that means you have 5% not shaded in, and that's evenly divided on each side. So that means you have 2.5% at the tails, 2.5%. So what you want to look for is a tail probability of 2.5%. So that is this right over here, 0.025. That's 2.5%. And so there you go. That is our critical value, 2.160. So this part right over here. So this is going to be let me do that in a darker color. This is going to be 2.160 times, what's our sample standard deviation? It's 50 over the square root of n, square root of 14. So all of our choices have the 700 there. So we just need to figure out what our margin of error, this part of it, and we could use a calculator for that. Okay, 28.86. That's our margin of error. And we see out of all of these choices here, if we round to the nearest tenth, that'd be 28.9. So this is approximately 28.9, which is this choice, right? Right over here. This was an awfully close one. I guess they're trying to make sure that we're looking at enough digits. So there we have it. We have established our 95% confidence interval. Now, one thing that we should keep in mind is this a valid confidence interval? Did we meet our conditions for a valid confidence interval?
Random, normal, independent.
And here we have to think, well, did we take a random sample? And they tell us that they obtained a random sample of 14 burritos. So we check that one. Is the sampling distribution roughly normal? Well, either if you take over 30 samples, then it would be. But here we only took 14. But they do tell us that the sample data is roughly symmetric. And so if it's roughly symmetric and it has no significant outliers, then this is reasonable, that you can assume that it is roughly normal. And then the last condition is the independence condition. And here, if we aren't sampling with replacement, and it doesn't look like we are, if we're not sampling with replacement, this has to be less than 10% of the population of burritos. And we're assuming that there's going to be more than 140 burritos that the population, that this popular restaurant makes. So I think we can meet the independence condition as well. So assuming that you feel good about constructing a confidence interval, this is the one that you would actually construct.
Which of the following is a 90% confidence interval for the mean battery? Okay, so let's draw out the thing again. Math isn't about memorizing. This is what everyone says. They say that math is not about memorizing formulas, but I think that it does help to memorize the formulas because then you gain an intuition and you gain a feel and you become comfortable working with them. You know what I mean? So I'm gonna do that anyways. Okay, so this is gonna be x bar. No wait, t int, which just stands for t interval. X bar, which is sample mean. Plus minus to represent left and right in a two-dimensional distribution. T star, which represents our t critical value. And this is S of some sort, and this is square root of n. Oh yeah, S is sample standard deviation. Okay. X bar is 9. Sample standard deviation is 2.07 within the sample. Square root of n. There were 6. .44 T 90% confidence interval 5 degrees of freedom 2.015 yeah must be 1.7. What is the confidence interval for this mean population mean? What is the confidence interval? It's the barbells. This is population. Oops. There's that. This has view. Draw a sample. X bar. Every time we do that, it's a different X bar. X bar, let's say 1, 2, 3. And there's 6 sample size. And the confidence interval is basically say what portion of the time when we draw many samples, what is our hit rate that within 2 standard deviations of our statistic, what's the hit rate that our true parameter, population parameter, mu, will be within 2 standard deviations of our observed statistic. And vice versa, that means the same thing. If I say an apple is 2 meters away from a banana, then the banana is also 2 meters away from the apple. It has to be true both ways. Okay, I'm yarning. It would be plus minus, the mean is 2.29, sample mean. I need to say sample or population mean because they mean 2 different things. Okay, plus minus 90%, degrees of freedom, 12 minus 1, 11, 11, 90%, 1.796. Square root of 12. Oh yeah, and sample standard deviation 0.2. Okay. Two 2.393. Okay, it must be C. So this or this, because of this part. Okay. 99%, 27. 2.771. Okay, 10, 15, 90% times 990, 1.833.
A group of friends wondered how much faster they could snap their fingers on one hand versus the other hand. Very important question in life. Each person snapped their fingers with their dominant hand for 10 seconds and their non-dominant hand for 10 seconds. Where if you're right-handed, right hand would be your dominant hand. If you were left-handed, left hand would be your dominant hand. Each participant flipped a coin to determine which hand they would use first. Because if you always used your dominant hand first, maybe you're tired by the time you're doing your non-dominant hand or there's something else. So here, it's random which one you use first. Here are the data for how many snaps they performed with each hand, the difference for each participant, and summary statistics. And this is actually real data from the Khan Academy content team. And so you see for each of the participants, for Jeff right over here, he was able to do 44 snaps in 10 seconds on his dominant hand, which is impressive, more than I think I could do. And he was even able to do 35 on his non-dominant hand. And so the difference here, the dominant hand minus the non-dominant, was 9. And then they tabulated this data for all 5 members. Now they also calculated
that's
summary
crazy.
statistics.
44 in 10 seconds.
But this is the really
That's
interesting thing right over here. This is the difference between the dominant and the non-dominant hand.
That's crazy. What?
And so what they did here, the mean difference, what they did is they took this row right over here, and they calculated the mean, which they got to be 6.8. Real data from the Khan Academy content team. And so you see for each of the participants, for Jeff right over here, he was able to do 44 snaps in 10 seconds on his dominant hand, which is impressive, more than I think I could do. And he was even able to do 35 on his non-dominant hand. And so the difference here, the dominant hand minus the non-dominant, was 9. And then they tabulated this data for all 5 members. Now they also calculated summary statistics for them. But this is the really interesting thing right over here. This is the difference between the dominant and the non-dominant hand. And so what they did here, the mean difference, what they did is they took this row right over here, and they calculated the mean, which they got to be 6.8. And then they calculated the standard deviation of these differences right over here, which they got to be approximately 1.64. And then we are asked, create and interpret a 95% confidence interval for mean difference in number of snaps for these participants. So pause this video, see if you can make some headway here. See if you can think about how to approach.
So we created a new distribution by getting the difference, and then we have a mean and standard deviation sample size. So since we have the sample standard deviation, we have the mean, our sample size is less than 30, we would use a t confidence interval just like we have been, but that's the reasoning behind it. And then we would just plug in the formula again, right? So we would go x bar, 6.8, plus minus to represent the upper and lower bounds of the confidence interval. And then we could go T star based on our confidence interval, which is based on the confidence interval and the degrees of freedom, which in this case would be 4 because 5 minus 1. And then we would just multiply that to the sample standard deviation over the square root of n. What actually is that? Standard error of the mean. Standard error of proportion? Is that a thing? Appears to be so. Okay.
Approach this. So what's interesting here is we're not trying to construct a confidence interval for just the fourth line. What you do, people want to look at
It's very straightforward. So we just minus new
the
stats.
square root. So instead it's ultimately 0, 3, 6 plus that. So let's do that again with the calculator. So 6.
Okay. That's fine. Drink some water. No, why do you go away? Dumb. $3.29. $571. 8.46. Close enough. Hold on. Plus minus. Wait. 8. No. 0 is not in the interval, so I'm so bad at this. Okay, so confidence interval. Oh, I wish I could draw. Okay, I'll draw with my hand. Confidence interval, 95%. Okay, 0. The null hypothesis is outside, so it's not. Unless it's double negative. Oh my god. Is this a valid conclusion? Yes. Oh wait, no. The makers of the website say that this interval provides strong evidence that using their program will cause an increase in the user LSAT score. Have no mean gain, so they have. Oh, dumb. Okay, break. Let's just keep going. It's like 10 minutes left. It's potentially above. Because the confidence interval goes from 380 whatever to 300, 400 something whatever. Well, this is so because, okay, so the p-value is the probability of getting your statistic given that your null hypothesis is true. So it's the area underneath the distribution curve or density curve, and a confidence interval, what we know about it, is that when you draw samples, when you generate sampling distributions, how do I explain this in plain language and make it shorter? I'm trying to think. I don't want to give a long-winded answer because then it also reinforces that it's a complicated thing for me. It's essentially a curve, right? And what's not within the 95% is 5%. So if you were working with the significance, oh wait, okay. If it wasn't contained in this 95% confidence interval, it'd be 5% or lower in terms of probability. It occupies that area of the distribution. 5% or lower means that if the null hypothesis is outside of that, the probability of getting your test result, I feel like this has to do with maximum likelihood estimation, but I could be wrong, is less than 5%. I feel so schizo trying to explain this. I have the intuition for it, but I don't know how to explain it in words. This is basically saying that between 122 and 126, roughly 2.24, 95% of the time that you generate samples from the population, it will contain the true population parameter oh my goodness. The true population parameter, 95% of the time when you generate confidence intervals, will be in between 122. No, wait, that's wrong. When you generate this interval, 95% of the time, it'll capture the population parameter. And seeing that 120 is outside of this 95% confidence interval, we can say that only 5% of the time will we capture, 5% or less of the time will we capture this 120 minutes, 2 hours. So it's safe to say that, okay, unlikely at 2 hours, it's probably higher. Oh my goodness. It's one of these. 9%, 4, 2.32, 95, 20, 2.093. They both 99 and 9. 0.25. D star is 95 and 6. 2.447. Okay. And stop's supposed to be sample standard deviation. Okay.
A quality-controlled expert at a drink bottling factory took a random sample of bottles from a batch and measured the amount of liquid in each bottle in the sample. The amount in the sample had a mean of 503 milliliters and a standard deviation of 5 milliliters. They want to test if this is convincing evidence that the mean amount for bottles in this batch is different than the target value of 500 milliliters. Let mu be the mean amount of liquid in each bottle in the batch. Write an appropriate set of hypotheses for their significance test, for the significance test that the quality control expert is running. So pause this video and see if you can do that. right, now let's do this together. So first, you're going to have two hypotheses. You're going to have your null hypothesis and your alternative hypothesis. Your null hypothesis is going to be a hypothesis about the population parameter that you care about, and it's going to assume kind of the status quo, no news here. And so the parameter that we care about is the mean amount of liquid in the bottles in
Different, not equals, okay, and then, yep.
the back opposed to the
Okay. Can we actually solve it? It's one of these. Longer. Different. What's the difference? Oh, it should be new. Less than. Higher. Okay, if you like this video, please subscribe. Help me pay the bills. No, I don't make any money off this, but it is fun to do math. And just log it down and fucking be accountable and stuff. Okay, bye-bye. See you in my comments.